I was lucky to meet Dan and his best friend Scott right off the bat. It was a great introduction, fun guys. I only recently got to meet Louie, colleague of Dan's here, but we're privileged to do that because I was sitting around and I saw some press releases. Something we do for this show, we gather press releases, and I saw this excellent bit of research all about how the universe got its structure, how this structure showed about. And as I'm reading it, I see Dan Kelson led this project, and I knew Dan was doing a lot of research on galaxies and at Carnegie. But Dan, this project is a little bit different than a lot of other folks' projects because you attempted to do something that folks might have thought about in the past, but didn't quite have access or the ability to do it. And the two of you are going to tell us about it. But thank you so much for joining us. It's a pleasure.
Thanks for inviting us on. I have to say, back in Santa Cruz, we were the ones who were lucky to have you, because once you got there, things, I think, got a lot easier for me. And maybe it was the espresso machine you brought to the office, and so I was able to have a lot of quadruple espressos every day. But whatever the reason was, we were really glad.
Yeah, no, it was a fun time, something special there we had with all the folks that are there. An amazing crew.
Indeed.
Thank you for joining us tonight to tell us all about the universe and what you've been doing with your time over the past, oh gosh, it sounds like you had a fair amount of time to gather all of this and put it together. Why don't you take over and start sharing
I will do that now. I mean, the fortunate thing at Carnegie is we have great people who come in, like Dr. Abramson was really half of the brains of this project, and I was none of the brains. So, I mean, in a lot of ways, we've been collecting data for years. So let me start this up and get the presentation going.
And then I'm going to hide myself. Well, I think if I don't talk, you won't see me.
That might be true. So what I think Dr. Abramson and I are going to want to talk about is something that many of you probably heard a lot about last year, because the Nobel Prize in Physics was awarded partly to Jim Peebles, who laid the groundwork for this sort of study as to how matter started clumping together in the early universe and continued clumping over the long history of the universe to give us the structures that we see today. And he laid the foundations of it using what are, in effect, very complex equations. And what Dr. Abramson and I really worked hard to do is try to simplify these equations into what would be an understandable story. And that's what I want to walk you through. So what do we mean by structure in the universe? I think this is really important because you look around and you see your house or you see your apartment, you see cars. You yourself are a structure left over from the dust from exploding stars. But what I want to talk about is galaxies that we live in and where our galaxy lives. So I want to talk about structure on large scales. Often we just call that large scale structure. So we live in a galaxy. Here's a lovely picture from South America in Chile, one of our mountaintops with our Magellan telescope in the foreground. And you can see towards the core of our Milky Way galaxy in the background. And on the left side, you'll see some fuzzies that are the Magellanic Clouds, small neighboring galaxies that are part of our local group. So we have many galaxies that are actually sort of in a region together. We're bound gravitationally, and this is structure on a particular scale. But our local group isn't sitting in an empty region of space. It's embedded in a larger group, a supercluster called Laniakea. And that itself is also embedded in even larger structures. And in fact, when we look on all scales, let's see if this animation will go through. Might get a little fuzzy, but what you'll start to see is this cosmic web where there are regions where there are more galaxies and there are other regions which are void or devoid of galaxies. And you just see this sort of webby structure that continues on all scales throughout the universe as we look farther and farther back. So the problem that has been looked at for now a few decades is that we know in a hot Big Bang universe, the universe started out after inflation looking quite uniform. In fact, if you were to take a picture of what the densities looked like, if you made a map of the sky at right after a few 100,000 years after the Big Bang, where basically atoms came together in a hot soup, it would look like this blue map. In fact, in this map I'm showing on this picture, there are the true density fluctuations of the early universe at that time. It's just that they're so small, at about a part in 100,000, you can't really tell from the small changes in the blue color. So our fundamental question really is how do you go from this to chunks of the universe that look like that. And the scales are actually roughly comparable here. So a lot of matter has to start clumping together. Those small regions that are slightly more dense than their neighbors start to pull in more matter. And here I'm going to show on the left, you'll see very slowly evolving a computer simulation using the basic equations that were given to us by Jim Peebles several decades ago. Slowly evolving over time, you'll see the density peaks pulling in more matter. But all the blobs of matter you see in here, they're not doing the same thing. They're moving around. In fact, there are some places where you'll see them moving across. Some get swallowed up. They're moving around each other. All of the interactions are just due to gravity. And we call these interactions nonlinear because you can't really solve the equations. They can only be approximated, very accurately, mind you, but approximated on supercomputers. The problem when we look at this is while it does a great job of mimicking what we see in the universe, it's hard to get intuition about what galaxies on average are just doing. How do we build a story out of what's happening here? And so I don't want to spend a lot of time looking at math, but I want to just point out that it starts out complex. And then we decided we could play some tricks, maybe cheat, try to pull out a story. And by doing some very interesting mathematical tricks, we were able to simplify them accurately and pull out a story. Because these equations, they're not solvable by human beings. You can't do them on paper. In order to solve the top one, you need to know the answer to the bottom ones and the middle ones, but you can't solve those without the solutions to the first ones. So it's just a big jumbled mess. So are these equations we have to ask ourselves? I think this is where Dr. Abramson's insights were really coming in, because he was reminding me time and again, these equations describe every movement of every piece of matter in the universe. But as astronomers, we observe the sky and we're not interested in the movement of every piece of matter. Because what do? We go and we look and we see light from galaxies. We can count up galaxies, we can measure them, we can see how far away they are. And these equations don't exactly tell us about the things we observe, about the things we really see in the sky. So they're great for doing computer models. As I showed you that movie just a moment ago. But again, those equations are not great for helping us understand, tell a story, find a way to explain what real galaxies in the real sky and the real universe have been doing. So what do we do? Well, we recognize, here's again, Dr. Abramson's going to speak a little bit more about this undoubtedly when I give him a chance. But I'm an old windbag right now.
Keep going.
Yeah, I'm keep going. There you go. We observe ensembles of objects, and I want to talk about what that means, because it means that as astronomers, in some ways, we're doing more sociology than physics at times. Okay, yeah. So what does that mean for us? We look at galaxies that are near us. We look at galaxies that are very far away. The ones that are very far away, the light took a lot longer to get to us. So the galaxies are being observed when the universe was younger. Those are different galaxies. Some folks in astronomy, many folks in my field, in fact, it's very disheartening, but many folks like to compare the distant ones as individual galaxies, compare them to the ones that are nearby, and think about how those distant ones evolved, how those earlier ones evolved into explicitly the ones that we see near us. But I'm going to swear up here on the slide, if you can believe. The problem with that approach is that every volume you observe, every set of galaxies you observe farther and farther away, they're not the same galaxies as we see nearby. We will never look far enough back that we see a galaxy that is even a young Milky Way, because the young Milky Way is, well, we're in the Milky Way. You can't go and step out at an earlier time. And so what that means is we have to think very differently about how to compare data of different data sets. So let me just jump ahead a little bit. What do we have to do? We have to then think how we compare ensembles. And when I say ensembles, that's gonna maybe trigger a few words for you. So what kind of words? Well, for one thing, if you have a collection of objects, you can find out their average properties. And then we should be thinking then about how the average properties of things evolve over time. Not how individual things evolve over time, but how the averages of things evolve over time. So we shouldn't take those equations that describe how all the matter moves in the universe. We shouldn't look at those equations and try to work out what individual blobs of matter do as observational astronomers. we should look at what those equations do for specific kinds of objects, and in particular for the averages of objects. Okay, so here are those ugly equations that I wrote down earlier that we can't even solve. So you look at them and you say, I don't know what that means. You know, each equation tells you something about the physics. One of them tells you about how density changes. Another one tells you how the velocities of pieces of matter change. The other one tells you how strong gravity is. They're not solvable by us. Okay, there's a particular way these fluid equations are described. It's called Eulerian. It's a fancy word. It's named after Euler. Okay, so now what we want to do though is think about how objects move and objects change. And what do I mean by an object? Maybe a galaxy or a region of galaxies, or where you basically just have a high density region of matter. These equations look a little simpler, or you know, they have fewer terms, and they're called Lagrangian fluid equations. They look like they might be a little easier to solve, but guess what? They're also not solvable. Okay, so they may look easier to work with, but they're, again, something we can't solve.
I'm going to chime in here just briefly and say, Dan, to folks like you and I, these might look easier, but to our audience, they're just like, oh my God.
Yeah, I mean, this is in the end. I mean, when people were able to write these down for the first time, they said they look easier, but they're still not solvable. So what's the point of them? I mean, I'm going to throw them away. I'm actually not interested in how an individual object changes, because guess what? As astronomers, we can't measure how individual objects change. I can't look at a galaxy and say, come back a billion years later and figure out what happened to it, or what it's, you know, what it did in the past. There's just no way to do that. So in that sense, these equations, even though someone might say they're complicated and someone might say, well, they're a little easier to look at, they're still nonsense for me. Okay, so what we need to do, I'm going to play some tricks now. I'm going to go I don't want to spend a lot of time going to a lot of math, because then we're going to be down to 0 viewers really soon. But you know, what we want to do is start with a simple, well, when I say simple for someone who looks at complicated equations. But you know, you want to take an equation like this, and the math tricks, I'm just going to flash kind of step by step, but not dwell too long. Okay, some of you who've seen calculus might say, oh, I kind of know what that looks like, but most of you don't need to care too much. We're just playing a trick where we're going to take an average of this and figure out what is the average rate that things change. So we're doing what's called an integral over the whole volume of the universe. That's how you average things. It's like if you wanted to average an average weight for all the people in the earth, well, you would just sum up all of the weights of everybody and divide by how many people there were, and then you would say that's the average weight. That's basically what we're doing in something like this. And so then it turns out there's a 200-year-old math theorem. This is where I get excited. Okay, I gotta stop for a moment. There's a 200-year-old math theorem called the divergence theorem, which says that if you can sum over an entire volume of everything, there are certain things that just become zero. And so we're going to lose all the really inconvenient parts of these impossible to solve equations. All the complexity is about to disappear. And so we're going to start looking at how these things change over time. And watch, turns out you're just substituting the gravity part here. And then you're just left with stuff that you don't even have to solve. Okay, so these equations may just look like a lot of nonsense, because they got numbers like 3/2 and a Greek letter omega, which is a number that we already know. So this is the fun part. I've got a 3/2, and I've got an omega, which is a number the cosmic microwave background tells us and other data tell us is about 0.3. So that's just a number. And the Hubble constant, well, we kind of know that to a few percent already. So that's just a number. And this A0 is just basically related to when galaxies started forming, which is we know that number more or less pretty well. And so like every number that would be in here, every letter that's here, any variable, like we know these numbers. All of a sudden we have like a short, sweet, simple answer for how densities change in the universe. That's pretty amazing to me that we were able to do this. There's a term that goes as the square of the time. So when galaxies started forming about 400 million years into the expansion of the universe, galaxies start forming. And then from then on, it's just the clock. What is the time since then squared? Tells you how dense regions are getting. It's pretty cool. And then there's another dependence. This is the really interesting thing too, is we're able to exactly say that if you had regions at early times that were, say, twice as overdense as another region, then this equation tells you they should grow 4 times faster. That's what we mean by the square. So the square is the number times itself. So if you had regions of the universe, if you added up all the regions of the universe that were 3 times as overdense as another set of regions, then they would grow on average a factor of 9 faster. Okay, this is a really interesting set of predictions. I mean, we just derived this. It's really neat. No one had done it before. And while this is very exciting, if I were a theorist, if I were just someone who played with math, I could write a paper about this and say someone should go out and prove this. Because it's a dead simple equation, right? And it tells us how dense regions in the universe that we find at different epochs should be comparable to each other, because we're comparing averages of ensembles of densities. All right. If I were a theorist, we would have published this paper. In fact, they could have done this 30 years ago or 40 years ago, but they didn't, because it didn't occur to anyone to play these tricks. And so we're left at this stage wondering, what did we do that might be right? Is it right? Can we check it? Because after all, I'm not a theorist. I don't know how to do, I'm not very good at math. It may look so far tonight like I'm an expert at math, but really this math that I just did, many people learned in college. This isn't like super advanced stuff, but it's still like any theorist in astronomy would know more math than me. But it just happened to be that I worked it out, and I have a lot of data on hand. I have a huge survey of distant galaxies, faint galaxies. Louis connected to this survey. A number of us at Carnegie, we were able to devote a lot of telescope nights because we have our own telescopes. We were able to collect a lot of very interesting kinds of data to multiplex. What does that word mean? It means we were able to collect data on thousands of galaxies at a time to build up a very big database. So this is a big image. It's like 3 degrees across. I superimposed a picture of the moon because this is one image with many colors. We got from the ultraviolet through the red at the Cerro Tololo Blanco 4-meter telescope using the big dark energy camera. And I put a little picture on the moon there so you can see how big the fields on the sky are that we're actually collecting galaxies over. So we got spectra and data and measurements of distances and masses for galaxies all across this image, like half the galaxies across this image. It's really cool. So we had to get massive amounts of what we call spectroscopy, and Dr. Abramson will tell you a little bit about that in a moment. We had an innovative prism. There's a picture in the upper right here, if you can see it. Some of you have looked through prisms before that disperse the light into a rainbow. This is a very weird looking prism. It's almost like a cube of glass. It weighs almost 50 pounds, but it's 8 little sort of triangular prismatic prisms for making those little rainbows. It turns out that in combination with each other, it makes very short little dispersed rainbows. So in the lower right, you can sort of see they get spread out a little bit, and allows us to just collect little spectrograms for, again, a couple of thousand objects at a time. And I think Dr. Abramson will show a few of those in a bit. Of course, when we get there, I think he'll have to tell me when to skip ahead slides. So, we had to map regions on the sky, design big metal plates that would let the light through from specific galaxies because we were targeting them in the infrared. We had to collect a lot of new images, process those data ourselves. It was a big undertaking, and it took us many, many years to collect the data and to process the data. Infrared imaging, again, we got from both the Blanco and the Mayal. That's up in Arizona at Kitt Peak. Let's see what we should do. I think we're coming up on Dr. Abramson's part. Yes. Louis, do you want to take over at this point?
Sure. You've control of the slides advancing?
Yeah, sure. Why not? If you want to tell me to do that.
Okay. What time are we? How much time do we have? Enough?
We have as much time as you like because we don't have park rangers closing the building on us in the park.
Okay, so yeah, I like whatever Dan says about his mathematical abilities, cut those down by a factor of 10 and you have my mathematical abilities. So I am incapable of thinking about the universe even in the what Dan calls rudimentary math, but which was math that I haven't done in 20 years. And so I have to think about it in terms of actual galaxies and objects. And where I come from, as Dan has been alluding to a lot, is that our goal here like we call ourselves astrophysicists, but because our data is so different from physics. I mean, in physics you can shoot a particle through an accelerator and make a video of it passing through your detectors and follow its trajectory and all this stuff. And all of that takes place over time. All of the, a ball flying through the air, an airplane moving through the air, someone, again, shooting particles at each other, all of the experiments that you did in physics class, time is a critical dimension. And if you didn't have time, if you didn't have a watch and you could drop a ball and time how long it took to hit the ground, you wouldn't be able to measure gravity. Astronomers don't have time. We don't have any of that because we only get to see these, as Dan was saying, these different galaxies at different distances. And it's true that the galaxies that are really far away, we're seeing them a lot longer ago. But because they're not the same galaxies as the galaxies closer to us, we just really don't have almost any of the access to normal physical intuition that like you got in your classes. So we have to come up with clever ways to try to disentangle the time dimension from all of these really snapshot data sets that we get. And my contribution to this work was trying to figure out, I suppose, if anything, how to tie Dan's math work into a kind of a story that's tellable through pictures of galaxies in different colors. So I'll walk you through how we learn some of that now. And if none of this makes sense, then I'm sure my email address is attached to whatever presentation this is. You can write to me. So. Okay, so as Dan mentioned at the beginning, we live in a galaxy called the Milky Way, but as he also mentioned, there are obviously many, many millions of galaxies, many billions of galaxies that are not in the Milky Way. This is a picture of one of them, and surely many of you know that a galaxy is comprised of things, a lot of things, stars in particular. So stars are the things that are giving off most of the light in this picture. This is one star, that's another, there's another in this galaxy. And it turns out that, press forward, Dan. Yeah, stars come in different colors. And this is pretty much critical. If really there's one thing that I want you to take away from this, so Dan's going to want you to take away why there's structure in the universe. What I want you to take away from this is that without color, we wouldn't be able to know if Dan was crazy. But because we have color, we know that Dan isn't crazy. And in fact, Dan's probably right. So stars have different colors. And this is where good old-fashioned physics comes in. It turns out that different colors of stars correspond to both different brightnesses, in that blue stars tend to be brighter than red stars, but more importantly, for what we were talking about now, different ages. So stars that are really, really big, they burn really, really blue because they're really, really hot. In astronomy, color goes the opposite way as in art. Blue colors are hot for us because they have high energy photons. Ultraviolet light burns your skin. It's got a lot of energy. So violet, blue are hot colors in astronomy. So stars that are glowing blue are big, so they're hot, so they die really quickly. They don't live long. They're young stars. So blue stars live maybe 1 to 10 million years. Stars like our sun live 1,000 times longer. They live maybe 5 to 10 billion years, and they're yellowish, as you know. And then there are yet more stars that live forever. None of these have ever died, and they're red. And what Dan is showing you here, Dan, if you could go back 2 slides, if you look at this plot here, it shows you this connection. What I'm plotting here is the amount of light given out at different colors. On the left is blue, on the right is red. And for big hot stars that don't live very long, you can see they put out most of their light to the left of the plot. And as Dan goes through to suns and even older stars, they put out more and more of their light to the red. So we have this connection, this intimate connection between color and the age of the star, which means that when we sum them up, then you can get some notion about galaxies. So as we said, galaxies have many stars in them. Imagine a galaxy comprised of 3 stars, a blue star, a sun-like star, a young star, a middle-aged star like the sun, and a very, very old star. If you add them together, what you get is this white line, the sum of all of their light. And that's what Dan was just showing. The instrument that Dan showed with that prism, it measures that white line. It measures that white line for thousands and thousands and thousands of galaxies, which means it gives you a very, very high precision measurement of the amount of light each galaxy puts out at different colors. And that tells us something very, very important about its stellar populations. So let's stop here. Why the hell do you care about stellar populations? Dan's been talking about averaging things. What are you going to average on? What is the thing? Dan said something about, Dan, you used weight, right? Dan was like, I want to figure out what's the average weight of people on planet Earth. Well, how are you going to measure a weight? You got to put someone on a scale. What would we like to average? What is the average quantities that Dan would like to track? Well, certainly we would like to track, what Dan was talking about in terms of an ensemble. How do we construct an ensemble? Maybe we just need to draw a box around things. But, in statistics, one of the things you're probably aware of is something like sampling bias, something where you're counting only certain kinds of objects. And if you don't correct for the fact that the kinds of objects you're counting may not represent the underlying population, you're going to get your answers wrong. Like if you only survey members of one political party in a survey, and you're trying to predict an election, it's not necessarily going to be right when the underlying population has people of more than one political party in it. So Dan has to make sure, we all have to make sure that when we look into space and we try to define an ensemble of galaxies, the thing that Dan's trying to describe by simplifying those equations, that we have a representative group of not just, space, but also things like mass and things like maybe even age. And that requires using this spectral information to ensure. So what Dan did is we go to the telescope, we get all this spectra. The spectra tell you all this stuff about colors, and colors are related to the ages of stars, but also, as we saw, their size. You may not remember that I said that blue stars are very bright compared to red stars, and that means that blue stars have actually more mass compared to red stars at the same brightness. And so if you want to weigh a galaxy, you need color information. So Dan's data from the telescope tells you something. It tells you something about the mass of the galaxy too. And that's really what we mean by representative samples, is we want a representative sample as a function of mass. We want to make sure we're capturing all galaxies, not based on their brightness, but based on a more physically interesting quantity, which is how many stars they have in them. Okay, so how do we measure that kind of a thing? The spectrum that Dan showed on the thing gives you the white line, and you can see that if you mix the amount of old and young stars, the white line's going to change. So you can see it goes from being, you can just see how the white line changes as we add different populations of different kinds of stars. It goes from being dominated by the old population, equally dominated, yada, 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 all this stuff. So if you have the white line and you have some sophisticated modeling, you can kind of back out how representative your galaxy sample is in terms of the ages of its stellar populations. And also, it turns out, as galaxies get farther away, you probably have heard of this term called redshift that Dan said. It turns out that you also need a color to measure a distance. I'm not going to go into this, but because the universe is expanding, and you all know about the Doppler effect of a siren moving away from you sounds lower in pitch than a siren moving towards you. All the galaxies are like ambulances driving away from us very fast, and the light gets affected the same way as sound. So light that starts out blue gets red shifted as galaxies are moving away from us, and it turns out they're moving away from us proportional to their distance. So you need color to learn distance as well. So color is very important. This is all by way of saying, if you want to do anything with Dan's fancy math, which I don't understand, you need colors, and everybody understands colors. So the job of an astronomer, this is it. This is my job. The job of an astronomer is to turn fancy math into dumb stuff like colors. And you can very easily see. So here's some data from Dan's survey. On the left is one galaxy. On the right is another galaxy. And this sort of black line with the red squares, that is like the white line we were just seeing in those other plots that we were just running through. And you can see, so let's overlay these two together now, that one galaxy has more light coming out to the left, and one galaxy has more light coming out to the right. And this means that one galaxy is filled with younger stars, and indeed, it looks like this blue. You can see it with your eyes. You don't have to be. Don't look at the plot. Look at the galaxy. You can see the blue light with your eyes. It's a young galaxy, and this other one down here, number 70, the one with the more light coming out in the red, is this spheroidal thing with no sense of blue light at all.
This is where I have to chime in and say the galaxy in the upper left is full of those hot young stars. We are here in Hollywood, after all, so that's the Hollywood of the galaxy.
It's a Hollywood galaxy. Yeah. It's a Hollywood galaxy. The one on the bottom is maybe, I don't know, a Reno galaxy. I don't want to be.
So the Reno galaxy, that is where I grew up, so it is appropriate.
So anyway, yes, Hollywood is a pretty cool. I live in Hollywood. I'm very happy to take the credit. So the point that I'm trying to make here is, though, all this fancy math, it does come down to pictures. You just have to apply a little bit of ingenuity. You need to know a little bit of a relationship between, for example, temperature and color, and temperature and age, and then you can back out from basically these pictures all sorts of wonderful things about the galaxy populations, and then you know how to make an average, and then you know what to compare to Dan's model. So yes, this is just re-encapsulating what I'm saying. You take 100,000 galaxies. You want me to stop, Dan? You want to go
on? I'll just show this. Yeah, why not? Go ahead.
You take 100,000 galaxies. You do some fancy stuff with them to say how much of them are 50% blue versus 10% blue, and same thing in the red. And then when you have all of this information, you can define an ensemble. And once you define an ensemble, you can do what Dan wants. And I'll shut up now, and Dan can go back to talking about fancier stuff.
Oh, I don't know. I think you do this really well. In fact, you have more insight onto many of these underlying foundations than I do at this point. But it's certainly true that once you know where everything is and how massive it is, then you can start to make maps. And we do special triangulation type maps, but really I think you could do it almost any way you wanted. This was a fast way to do it for us. But we have
up here just to make sure I understand what's going on and make sure all our viewers understand. So what you did is you went in and looked at all these galaxies, you measure their colors, and then from the colors you can learn what kind of stars have to make up those populations that are within that galaxy. So we have so many young stars, so many middle-aged, so many old stars, and then that tells you the total mass in the starlight in those galaxies and how those galaxies have grown. And then you average this over time, and then Dan can make maps like this that's telling us about the density growth. Is that what I'm getting from here?
That's right. So let me show you here on the left side, right? So we have a region of space that's about 7 megaparsecs on a side. What is 7 megaparsecs? That's like 21 million light years on a side, right? And there's a lot of space between these points. Each of these points is a galaxy that's has a certain amount of mass, and these are kind of far apart. There's a lot of open space here. So this is a region which is not very dense. But what we can do is we can kind of draw a box or a funny irregular polygon and add up the masses of these galaxies, and then say, oh, well, we know in this space how much area there is and how much mass there is. And well, we all know how to make a density from an amount of mass divided by whatever volume we're looking at, which is just area times the depth. But if you look in the middle, these galaxies are closer together here. So the density is going to be higher here. And even on this side, where there are lots of galaxies, you can see there's this sort of general pattern where there are lots of galaxies very close together, because the scale in all these boxes is the same. It's still 21 million light years on a side. And so when you look at this, you see all these galaxies very close together. This is probably a very tight group, maybe like the local group, but when the universe was younger, something on that scale. And so it gets very exciting when you can start to do this, because you can then, for a whole region of the sky, or many regions of the sky, as much as you've observed, is look at what the distribution of densities is. And so I'm going to make a stupid plot here, which is a cumulative distribution function. 3 people might remember what that is from school. So what I want to say is this along this axis is what fraction of the sample, what fraction of the densities we've measured is less than the number that's along this axis. Okay, so what I want to basically jump to is up here, right here, which is at the high percentiles, Some of you who might have had kids, you take your kids in to get weighed, and the doctor says your kid's at the 75th percentile. That means that your kid weighs more than 75% of the other kids of that age group. But here I want to look at like the 98th or 99th percentile, regions of the universe at early times at 99th percentile, on average for this density. But at later times, many billions of years later, they have an even higher density. So they grew in density. They got more dense. Boy, that's getting to be a muddle.
So really what I'm taking from this is that if you start with a high density, your density is going to grow even faster than somebody that has a medium density, and the medium density grows faster than somebody at a low. In other words, those lines are getting more spread out as you
That's
get
right.
to the higher percentiles.
Exactly. That's exactly what you can see here, which is very exciting because our math predicted something like that. And so what we want to do is take these curves, take these data, and try to work out, did this amount per unit time work out to be the same as what we derived in our math? What about this amount? What about this amount? And as you see by your eye, Dr. Reitzel, there's less growth in density here, much more growth in density here. I don't want to spend a lot of time on this part, but this is an interesting side here. These are the underdense regions, and they actually have densities that go down with time. I didn't talk about that earlier in the math, but that's what we expect if gravity is pulling material from underdense regions and moving that mass to where the densities are higher, because where mass is, where overdensities are, the gravity is stronger. And so in all, all of this should give us a very simple picture that hopefully agrees with the math we derived. Okay, so what I want to do is say, we can look at specific points along the curves I just made. So for example, at different percentiles, you can see the density. Oh, that was a terrible way to draw that. The density goes up with time. So this is early in the universe, early, and this is later in the universe, here, later. And the highest density stuff seems to grow much faster than the densities that are here. That's a very slow growth. And we can measure what those rates are. And in fact, from these data points, we get this. Let's see if I can change color to blue. You see these sort of contours here that look like this on this side. I don't know if you can see that. But basically, the data points give us these inferences for the rates of growth. And what the math actually told us is this diagonal line, like right through the data. See, to me, that was extremely exciting. This has the exact slope.
It's a big deal. It's a big deal. It's a big freaking deal. That's a big deal.
Yeah, no, this is. For the folks out there that don't quite see what's going on here, what this is saying is that the equations, the theoretical work that was done is matching the actual observation and analysis. So this is a big deal. This is the payoff part right here.
This is the payoff part. So what I want to do, though, I want to back off for a second because we spent a lot of time on math. I'm showing very mathy things in this plot. So what I want to do is say that for decades, astronomers, theoretical astrophysicists have been running computer simulations that really do a really cool job of making movies of what structure looks like in the universe at different epochs. But not once did any of them tell us, regions early in the universe that were 3 times overdense than other regions are going to grow 9 times faster. Nobody ever could say that. That's where this is why what we've done, I think, to me, has meaning, because we've now abstracted all of that sophistication, all of that complexity that you could watch in a movie but not fully understand. And we can now tell a story. And we can say regions early in the universe that were a factor of 2, more overdense, I should say, will grow a factor of 4 faster than the other regions. And if you happen to be in a very rare region that's a factor of 5 more overdense than another set of regions, you'll grow in density a factor of 25 faster. Like, we can tell a story now, but now I'm understanding what happens and how galaxies in those regions are going to get fueled that much more quickly, and why galaxies in those regions will actually probably exhaust that fuel much more quickly. We can actually start to tell we can explain things better now. Whereas before, you'd look at a simulation, as excellent as they are for reproducing the things that the designers of those experiments wanted to look at. As someone who studies galaxies, I wanted to know what the what the galaxy economy is, or what the climate is. I mean, the difference here is if you asked, maybe it's if you asked somebody to learn about forests, and maybe the physicists would say, well, I'm going to do a computer simulation of a forest. And they would then say to themselves, well, I need to make a computer model of a tree. And then I need to put a whole bunch of those together. But really, I just want to know what the forest is doing. And maybe if I just know what an average tree does, because the rates of growth are going to fluctuate from year to year, but there's some average that follows some other principles or laws, maybe that's all I need, but I can tell a story about the forest and not be lost in the details of what the trees are doing. Now, that's a bad analogy. Well, I like that analogy sometimes. Yeah. Now, there's a curve in the middle of this page here, which I'm just going to show as this cumulative distribution. But that's basically, if we look at it in a way that many people are used to, it just looks like a bell curve of the initial density distribution. And that's actually very exciting, because the initial densities that we pull out from our data basically look like exactly what we would have expected from the early universe after the cosmic microwave background. Now, the other thing we can do with these data points here is we can actually look and see if the time growth here of these points not just goes as the density squared, but we want to know, we can fit all of these curves and ask if they go as time squared. Okay, so our prediction in the math was that the density should grow as the square of the time. And that's time, remember the square of a number is just the number times itself. So it could have been a different exponent, it could have gone at a different rate according to our data, but it didn't. Our data exactly followed the curves that we derived. I mean, this is a big deal to all of us, because now we have a story, we can write things down, we can actually explain these in a way where we don't even need the big computer simulations to understand stuff anymore. So I guess that gets me to sort of a bit of the summary here. The equations that were laid down a few decades ago, that won the Nobel Prize last year, right? They're reducibly complex. They give us the full picture that you see in computer simulations. They've been the bedrock of all theoretical astrophysics for decades now. They're still of value. I'm not trying to make those go away, but they do, from my point of view, obscure the stories that we're trying to extract from our data. So what we've done is we've cheated in some ways, right? We took these intractable equations and we played some tricks to basically get the equations to say what our data should be doing. How do we match up the expected physics with what is happening in our data? So all of the difficulties of the equations just fall away because of the simple tricks that we were able to perform. And then out pops these stories that exactly match our data. And of course, it took a lot of data. So while we could have made these predictions decades ago, someone could have, the data really couldn't be gathered until probably the last 10 years. But we did take about 10 years to collect the data and analyze all of that data. And it was a tremendous amount of work. It took a team. I didn't list everybody's name. There were 6 or 7 other people, other senior staff members, a couple of other postdoctoral researchers. Dr. Shannon Patel was integral in the formation of this particular survey and this kind of work. But it's been incredibly rewarding to be at a place where we could take the time to really work through what it is our whole field has been trying to do. And so I think when Dr. Abramson came to Carnegie, he was able to really sit down with me, and we were able to come up with a new path forward. So in many ways, it's pretty exciting to have done this and to really try to lay a groundwork for a new way of doing astronomy. So I think there's a movie here that can show, and what will happen in principle is we'll start with the microwave background, this picture of it, it's solid blue, but over time, according to sort of early structure formation theory, the amplitudes of the peaks will grow with time. And at about a redshift of 10, what happens is galaxies will start to form. And here's the density field growing in early galaxy formation. And at some point, very soon, here we go, you get the observed things where we're going to get slices through the data at different redshifts here. And of course, the field narrows here because our data only take a finite extent in angle on the sky. And so, we might be looking at a field that's 3 degrees across, but the farther away one looks, that's sort of a bigger metric scale at those distances. So that's sort of the picture of how structure grew in the universe. And again, we already are able to tell the story about how structure grows on average as time squared and at rates proportional to the initial densities to the power of 2 as well. It's actually pretty amazing that we were able to distill what giant computer simulations that follow the detailed laws of physics. We were able to distill down out of all of that this incredible story of how gravity feeds and grows the structures that we observe in the galaxy distributions. And those stories have remained opaque, at least for a few decades, but we've opened it up now. So I think that's really the remarkable story here, is that we were able to do some of that math and have the data to confirm it. And of course, I have to thank you for letting us talk so long about this.
Oh, absolutely. Well, thank you. Absolutely. Thank you for joining us. Give you a little round of applause there. I know we don't have an audience for you. I have a question right off the bat. And if anybody out in the audience on YouTube has a question, you can go ahead and type it in. We'll get to them here in a second. Have you had a chance to go in and analyze any of the large simulations like the Illustris survey or any of the others? Does their density grow at the rate you predicted? Were there guesses?
So this is very exciting. This is very exciting. So not many computer simulations have the volume. So this is really an interesting problem. There are a few simulations that have a large.
Why don't you share your screen as well, Dan, so we can
see.
Yeah,
we've
been seeing you this whole time. I know you had some internet problems in your iPad. Thank you for hanging with us, folks.
Zoom and go back to Zoom.
Yeah, thanks for being patient with us there. I know you couldn't see Dan that whole time, but the way, anyway,
you don't need to see my
like you said, we've been having internet troubles all along and with all the other stuff. Yeah, thank you for bearing with us. But Dan, so did anybody go into these surveys and have they been doing things right? What do you think?
So this is a really interesting question. So, our data set probes a volume that's almost as big as the Sloan Digital Sky Survey volume. And it takes a volume that big to really do this. But not many computer simulations are both big enough and have the resolution. And so let me talk about what that means, or Louis can talk about what that means. But in effect, computer simulations are run on big, massive supercomputers that have a finite amount of memory and processing power. I mean, they're not infinite in size. And so you may only be able to run a few billion particles for a certain number of billions of years of simulated universe lifetime. And so then you have to ask yourself, if I'm going to do a volume that's many gigaparsecs, cubic gigaparsecs in size, then each particle that is in my simulation is too massive to probe the kinds of scales that you need to actually do this math. So there's at least one simulation that sort of manages to be in a sweet spot, and it's this multi-dark simulation out of Denmark, I think, MDPL2, if you really want to look it up. And it's really, it was really interesting. So they have some mock galaxy catalogs that they produced for that simulation. So I was able to download those while we were writing this paper. It's in the back of your mind thinking, I need to be checking this somewhere because someone's in a computer run those laws of physics, so they better agree. And sure enough, when I analyzed the fake galaxy catalogs out of that simulation, it was beautiful. It's like right on top of it. And obviously that's incredibly rewarding. And there are some interesting differences. So I suppose I could give you a little inside baseball on that. Like, you have to do this with a mock galaxy catalog. So what does that mean? You can't just look at where the dark matter particles are. You gotta turn that simulation into something that would look like, here's a galaxy, and has starlight. So there are aspects of the simulation that are just wrong. So if you do the analysis with the starlight of those fake galaxies, it doesn't quite come out right. But if you add up the baryonic mass or add up the dark matter mass, it does come out right.
Okay. So they're not getting their star formation right.
Correct.
Yeah.
That's right.
A little
and I don't want to write that
mass
paper yet. Yeah, exactly. Now Illustris is too small. And that's a really, I've been wanting to go with, I think it's still just too small a volume. And it's a problem.
I can see that. Why don't the rest of our All Space Considered panelists come back here? Laura and Patrick and Tony, if you guys have any questions, take a look here in our, it doesn't look like anyone in our YouTube stream has typed in any questions. Most of our audience can't.
We do actually have a question from the YouTube stream.
Oh, do we? I missed one. Okay, so what is
I don't know if it's a really easy question to answer or a really hard question to answer.
Hey, Louis, you take it.
Know why you're using time squared when you are looking at the kind of the evolution of these galaxies. Why are you squaring the time rather than just looking at time normally?
Well, we're not looking at time squared. We're looking at, if you really want to be technical, we're actually only looking at distance. It's just the distance and time are related because of the age of the universe. So what we're doing is galaxies exist at different distances. It turns out that because of the universe expanding, those distances happen to correspond to certain slices at certain times. And you can take slices through you can just collect all of the galaxies at a certain distance, and they represent the picture of the universe at that corresponding time. And what you do is you just measure the densities there. So you just go and you count the galaxies, you draw boxes around them, you say 5 galaxies per light year. That's not the right scaling, but 5 galaxies per light year here, 10 galaxies per light year later. And then the time between those two, and it turns out that they're connected by that difference in time squared. So it's not that we're looking at time squared, it's that when you go to different times and you measure the density in corresponding ensembles, as Dan was saying, the densities in those ensembles happen to change at a rate that is proportional to the difference in time in those two slices squared. So if they're
more of a result than something that they chose to do.
Yeah, no, great answer. And perfect. Thank you very much.
And I want to add a little thing to that, because this is something that Dr. Abramson used to also remind me. When you take a basic physics class, either in high school or college, you learn in one of the early parts, you throw a baseball in the air, follows a trajectory, it goes up, comes down, and when you write the equation for that trajectory, because it's gravity, that goes as time, the height goes as time squared.
Right, your acceleration.
So this is exactly analogous to that. So your acceleration is constant, it's just gravity, g, 9.8 meters per second squared. But in the end, when you turn that into a velocity and then turn to a distance, that height goes as just time squared. And so, this in many ways is just the same physics. It's just that we're adding up a lot of baseballs and saying, what does the average baseball do?
Perfect. No, I think that was a great answer. And we'll let you know if we have any more from the chat. But for now, I'll let you guys talk yourselves.
Okay. Thanks, Brandon.
Thank you. And again, thank you, Louis, for help, clarifying all of the bits that I find very hard to explain.
So I have a quick question for you, and that is, you said this was 10 years and this vast volume of data. What's your next step? Or do you tie this one up and turn to something else altogether different?
Which one of us should start answering that? But there's.
I can start. Good. I can start. So, I think what's important to understand is that science is not. So science is, certainly astronomy, is very badly misconstrued, I think, in most representations in the public media. What Dan has done, and I think what unifies most great scientists that I know, there are many great scientists at Carnegie, and I think what really makes scientists, good scientists that move the field forward, what their thing is they know how to take a problem that looks really hard and that people have been approaching from one direction incrementally, and then just kind of move the camera around and see that actually from a different direction, it's actually much easier to solve. So it's not actually the smarts. It is much harder. It would take a much better mathematician to solve the equations that Dan showed way, way, way at the beginning than the equations that Dan and I actually ended up solving. But what Dan's moment of creativity was realizing that you don't care about the baseballs. You care about the average of all of the baseballs. I don't care about your individual cells in your body. I care about you as a human and what makes you do things. And I'm going to just forsake describing the cells. Everybody's been trying to describe you from the cells up. I'm going to forsake it. I'm just going to not worry about the cells. And when you do that, it makes certain things much easier. It makes the growth of structure much easier to understand. The question is now, so the natural progression would be, okay, let's take the next level of refinement. What are the galaxies in the volumes doing? So you've described how the density, you've described how the number of galaxies per box evolves. What does that actually do to the galaxies? What corresponds, how does that fact influence the growth of the galaxies, which is what we actually see? And that is the question that came up earlier when David was saying the simulations get the star formation wrong. Well, the simulations get the star formation wrong because they have asked that question. They've said, okay, we know how gravity is working. What assumptions can we layer on top of that when we run through a computer enough times produces things that look like real galaxies? So to me, the next step is we have to abandon that. We have to take another approach, another step like Dan did here, which is to the next step is we have to ask, where is the next step coming from? It's not, what do we do next? Like, obviously there are galaxies. We haven't explained galaxies. But to me, the next step actually has nothing to do with galaxies, and has nothing to do with data, and has nothing to do with even necessarily astronomy. It has to be, we have to think as a group, what are the right kinds of questions to ask of this data set that we have? The data set is different objects at different times. We don't care about the different objects. We care about how an object evolves. That's what the physics feels. How do we take this data and somehow look at it with the proper glasses so that some aspect of that question that we care about becomes answerable? So the next step to me is all about thinking hard about how we actually look at these data, as opposed to what is left in the data that we have that we could explain. I'm sure that question wasn't very, very intelligible to most people. Like, I don't think we're going to figure out why some galaxies are blue and some galaxies are red. We have to figure out a way to ask that question that is easier to solve than the way that everybody else has been asking it to date. And that's just going to take time and maybe some beer. I don't know.
That always helps. I was thinking earlier when you guys were talking, and especially around that conversation about, so they got the star formation wrong, how much it felt like being at a bar at a conference with a beer or two and this kind of conversation, except now, after a beer or two, then ramp it up. And as to the point where people are at, on the verge of shouting, then that's kind of, now you get the feel of a scientific conference.
That's right. I think you're right. I mean, and Louis brings up a really interesting part of it, which is really thinking about what those right questions are. And, for decades now, there's just been that layering of assumptions about how stars form, put them in those assumptions into simulations. And maybe what we need to better understand is, what would it take to know or learn that we got any of that right? What is it in the data? What is the information that's present? And I think, he and I are fortunate to be at Carnegie at the moment because, the pressure is on to simply think about that. The pressure is not on to write, more incremental papers, which are important in their own right for many other reasons, but for them, where we are, we can take time and think about, what do the data mean? What is the information that's present? But really, what are the questions that we're trying to answer? And so, you asked the right question for us. It's like, what's the next story we want to try to uncover? And I think it's not obvious to us. It's just not obvious yet.
I think you have some interesting populations to compare. If you take an object that's at, half a time earlier, but at a density that is double, it should be the same as you can compare things at different ages and different densities, and the populations within those should look similar, because you have similar growth in those times. Now, of course, you're going to be in different parts of the universe, but still, there's something interesting in there to pull out. I don't quite know what, but
I think you're right. I mean, there's no question that what you need to be able to do to compare any sets of galaxies, pardon me now, is you then have to look at these densities as ways to locate the full fair ensembles that you can compare from one object to the next. I would say we have a complication in doing that with the data we have, because ideally, what is it you need are measurements of the matter density that are not connected to your starlight measurements. Because, right, we've measured masses using the starlight, and then if we're turning around and saying, but in this region where we have a lot of starlight, we have galaxies that are, say, on average bluer, which also generate more starlight, it can become a little too circular. And so there are some surveys ongoing that are using a technique called tomography to actually look at, right, the sort of lower density baryons as a tracer of the dark matter density. And I think as those tomography surveys really come online, there's one being done at Carnegie right now in a small field, but when the prime focus survey gets done at Subaru, that may provide a large enough field with enough tomographic density and measurements to then start to say, okay, we have overdensities here. What are the galaxies like there? And then you can start to then dovetail that to this map.
Yeah.
So I'm hoping we laid some of the foundations for that kind of, approach, and time will tell. You don't really know yet.
Now, final question here from me. Are you planning to do some pointings? Now, I want to say it's the Roman telescope. Are you planning on doing any pointings with that? Because how many would cover your field? It looks like 6 pointings maybe, or something like that.
Well, I think, the GTO survey data will already presumably be, the guaranteed time observations, they're already going to have these massive legacy data sets that I think people should 100% dive right into doing this sort of analysis. They may find where my stuff breaks down. So then the question just becomes, do I want to do that? Or maybe I should let Dr. Abramson do that, because, it's his job to show where I'm wrong.
Exactly.
And that is the strength of science. And it kind of goes to what you were saying. And I guess I was calling you Louis earlier. So Dr. Abramson.
I'll call him Louis too. It's both.
But
he's younger than me, so.
About the nature of science, because that's the whole point. Isn't necessarily to, it'd be great but even if you have aspects of your conclusions that need to be modified by what's learned next.
That's right.
It's the next, level in the scaffolding, and that's how it all works. So that's a good thing.
Yeah, it is a great thing. It's a good thing.
It looks like Tony has a question.
Yeah, I know we didn't do a story tonight on some galaxy that was discovered that looks like it's far more evolved, I think, than somebody was expecting it to be at its great distance.
Oh,
yeah. So I'm just curious, does your work suggest that we have a lot to learn about what to expect at great, near just after the Big Bang? Is what you're doing applicable to what our expectations might be, what we'll find with James Webb, for instance, looking?
Louis, do you want to start with that one, or do you want me to write? I was going.
Well,
I'm happy to start. I think one of the things we saw here, I'll just inject a little technical bit, right? So the densities grow as the time squared. What does that mean? That means there is something called a stochastic process that is matter growth. And I know it's going to sound a little technical, but it means that the rates at which matter is accreted onto nascent galaxies is of a particular form where the growth of galaxies just occurs very rapidly. So when star formation begins in earnest, when the universe is a few 100 million years old. Now, maybe James Webb will show that it started when the universe was 250 million years old or 325 million years old, and that will be important information to know. But what this math shows is that the growth of stellar mass, the growth of stars and galaxies, occurs so rapidly that really almost right away you will see more massive galaxies than people have thought about before, and even more evolved looking ones than people have thought about before. It's a natural consequence. Yeah, go ahead, Louis.
No, I was just to turn that into way speak, it's not surprising. None of
Yeah.
this galaxy, the existence of this thing is neither surprising nor, I mean, I'm not even sure it was unexpected under the old paradigm, but it is, we should find, it's rare, but there's, as the universe is big, so we should expect to see many more of these objects from James Webb. And in fact, we should expect to see them as a function of density. Like, they should tend to live in environments with slightly more galaxies than other things because of what Dan showed. Environments grow fat, more anything, where there's more stuff happens. So you should expect to see these things slightly biased, we call it, towards high density regions, but you'll find them in low density regions too, just less of them. So I mean, we haven't gone through the rigmarole of predicting how many of these things James Webb will find, but this, the existence of this thing is not terribly surprising to me.
Thank you.
The natural consequence of having so much grow so quickly is that the stuff that stars make comes out more quickly and sooner, perhaps, than many people would have just had a gut instinct for. So there's a lot more dust production. There are heavy elements that get produced right away through the supernova in those systems. And right away, you see galaxies almost as massive as the Milky Way, in really just a few 100 million years. It's then suddenly like, wow, And
Yeah. I want a prediction of how many Pop-3 stars there are.
and how many direct collapse black
More
holes
than
there are.
zero.
Yeah.
More than zero.
Yeah, I don't think I've worked at that scale yet.
Yeah, not quite. So, well, this has been super,
That's
super
good.
interesting.
Thank you, Dave.
I just want to make a quick comment from the chat because I've had the opportunity finally to take a look in the chat. And Dan, there's a comment that how lovely it is to watch you talking about the cosmos and see the sky, the night sky behind you.
Oh,
So yeah, you maybe have not looking at the set decoration you have there, but it's very nice. And,
it's a little overcast and hazy. You missed the full moon rise earlier, though. It was lovely.
yeah, and we've missed a lot. We've had some clouds at night.
Yeah.
Nice. And Louis, you said you're in Hollywood, so I'm imagining you're kind of down in the thick of the lights and the what is it? Lights, cameras, and action.
I have to sleep with a. Do I have it here? I'm in my bedroom. I have to sleep with a mask on because there's so much light pollution. But yes, no, I'm by the lights and the cameras and the action. We have the Walk of Fame is in my little jurisdiction here, so we're yes, we're right in the thick of it. But
yeah,
I like it.
So before we say goodnight, Brendan, are there any questions? I didn't get all of the questions on here, so if you have any.
Not any big ones that I saw. We answered a few. The moderators answered a few as the night went on for just kind of the basic stuff, but I think we covered most of the big ones.
So since it's very late, and this has been a very intense and dense couple of hours, but so much appreciated by all of us and all of our audience who, which we still have a pretty significant audience hanging in all these hours later, which is nice. And speaks to people's passion for the kinds of things that you guys are doing. So we really say thank you for coming.